Thank you for letting us present our results at this very important conference for us. It was, in fact, the first conference I ever came as a PhD student in year 2000, I think. And now we have so many nice results and new faces. And we really see that this field is going to very much progress in the next years. So our contribution is regarding another exotic atom, antiprotonic helium, and yet another one, pionic helium, which we carry out at CERN and at PSI simultaneously. So antiprotonic helium and pionic helium are fundamental three-body, long-lived, as an exotic atom, as an exotic hadronic atom, Rydberg helium atoms. So you can think of them as the antimatter counterpart of the Hd+, and even the mesonic counterpart of the Hd+ molecular ion, for which there's been a lot of progress in the last years. So it's essentially a helium nucleus and one s electron, okay? And this is attached, of course, with a really strong ionization potential of 25 electron volts. There is an antiproton in a circular Rydberg orbital, which has a principal quantum number of around 38, an angular momentum quantum number of around 37, that this has a diameter around 100 picometer. And such a wave function is localized significantly away from the nucleus, as we heard from Nancy. And then in this case, in our atom, the electron doesn't go away so easily. So the electron is retained, and this is the unique aspect of this atom compared to many other exotic atoms. And this causes the atom to have a mean lifetime of up to 4 microseconds and longer in high density gas targets. It's in fact the hadron, anti-hadron bound system with the longest lifetime that can be readily experimentally produced. A pionic helium atom, which we've never discussed in this conference before, at least from our group, is something with a principal quantum number of around 17, angular momentum number of around 16, and it has a lifetime of 7 nanoseconds. This is barely enough to do laser spectroscopy, as we will show. So the point is that, as we have heard, this really nice non-relativistic QED and the complex coordinate rotation calculation methods, this means that these atoms are in fact not strictly bound states. They are existing somewhat above the electronic continuum in a way, so that it is unstable against the electron being ionized and the antiproton falling more deeply into the nucleus. So these theoretical calculations allow you to study such an thing which is kind of quasi-bound with a precision of around 1 part in 10 to 11 or so, theoretically, by including m alpha to the 7th scale QED corrections, as perhaps the next speaker will talk to you about. So in principle, it is approaching, I should not say it's the same level, that is too insulting, but it's approaching the same level as the theoretical precision of two-body atoms. And for these Rydberg states, it's less sensitive to nuclear effects. So this lets you study all kinds of nice fundamental constants, CPT symmetry, and limits beyond the standard model. This is a kind of fifth force effects that not us, but groups centered in Mainz. Also, this university, Amsterdam, has introduced into this field as a new physics motivation for doing this kind of physics. So, as I said, the angular momentum of the antiproton is here plotted between 30 and 31. The principal quantum number is here plotted. And when you just put an antiproton into helium, where the electron, one of the electrons goes away and you produce this atom, and the antiproton, some fraction of it, happens to find itself into one of these red line states, which are kind of stable against all kinds of OJ decays and radiative decays and so on. And the really nice characteristic, which is a kind of coincidence, is that these radiative E1 transitions exist exactly in the visible range. So then you can fire a laser beam at an atom where the antiproton is populating one of these blue states, depopulate it and reduce its angular momentum of the antiproton sufficiently so that the antiproton, the three-body system's angular momentum is close enough to a two-body state. And then what happens is that the electron goes away and we are left with a two-body system, okay? So the electron goes away and this being charged attracts the surrounding atoms in the experimental target, and then you have annihilation. So if the laser, if you're producing this atom and if the laser is in resonance with the atom, then you will see an annihilation, sort of annihilation on demand. So this community has calculated the two-loop self-energy corrections and so on for the two-photon transition of this atom already 7-8 years ago to very high precision. This kind of method, again, as for other atoms that we have heard, is based on non-relativistic QED, where you calculate the non-relativistic energy using a kind of Schrödinger equation, and then adding the higher order corrections as a perturbation. And right now, we have this situation where the experimental precision is at this digit, the uncertainty to the QED precision is at this digit, and the higher order effects due to hadronic corrections, QCD corrections, are in fact smaller than the precision over here. So this really motivates us to try to improve the experimental precision. So until 2018, when CERN shut down once for the LHC upgrade, our experiment looks as follows. The antiprotons came in. There was a radio frequency quadrupole decelerator, which was about 3 meters long, which decelerated the antiprotons coming from the antiproton decelerator, which is about 5 MeV. That's too high for doing atomic physics. Okay? So you decelerate them to 70 keV using this device, and then you introduce them into a very dilute cryogenic helium gas. Then you produce these atoms, and then you irradiate the atoms with 2 counterpropagating laser beams, which have sufficiently high power to induce these Rabi oscillations in the antiprotonic states before they annihilate, because as I explained, it has a lifetime of around 4 microseconds only. The usual quantum optics techniques using frequency combs and so on to have high spectral resolution, high spectral purity, in addition to high power. So what we have studied two photon transitions by arresting the Doppler width, reducing the Doppler width of these resonances by irradiating the atom again with 2 counterpropagating laser beams, so that if it's a single photon transition, you get a broad resonance. With 2 photon transitions, you get a really narrow resonance with 4 peaks, corresponding to the fact that the antiproton and electron in this atom are both spin 1/2 particles, and therefore you have the hyperfine structure. We can also cool down the atoms by allowing it to collide with other cold helium atoms, and therefore you are also able to reduce the Doppler width and see narrow resonances even in the single photon regime. And then from comparing these results with QED calculations, one is able to determine the antiproton to electron mass ratio. Our result is here with a precision of 8 × 10⁻⁻⁰. One can compare it with these extremely nice experiments that we have heard already. One for the Mainz Heidelberg GSI experiments for hydrogenic carbon and oxygen in a pinning trap. The other type of experiments we heard 2 days ago for the HD+ molecular spectroscopy. They are really good resolution, precisions. And well, we have not discovered CPT violation, but you see that if we can improve this precision, we can probably contribute to this effect in terms of improving the proton to electron and antiproton to electron mass ratios. Also by comparing combining our results with the really nice results from BASE and the trap collaborations, one is able so far to determine the antiproton to proton masses and charges separately to a precision of 5 × 10⁻⁻⁰. So this is again results coming out of this community. as we have heard, the inverse square law of gravity has been proven to a sensitivity of only 10 to the minus 10 in lunar ranging experiments. It has not really been tested at 100 micron length scales because there's all kinds of experimental background difficulties. The fact that the antiprotonic helium atoms and also the Hd plus molecule agree so well with the experiments makes us sensitive. Well, we are able to set upper limits and to say, well, it's about 10 to the 28, at least 10 to the, not more than 10 to the 28 times larger than the Newtonian one, these Yukawa type fifth forces. So if we can improve the precision of our experiments, also the Hd plus is the same thing, we can probably go from 10 to 28 to maybe 10 to 25. And well, this is kind of interesting to constrain several theories. I think this is the first author is actually from this country, from Kaukau. They have determined upper limits on the coupling between an antiproton and electron spin sensitive forces to axions and other spin 0 or 1 bosons. Well, in terms of the possible mass of this hypothetical particle, which goes from, for example, 0.01 electron volts to 10 to the 4 electron volts. So now we have this machine and it's operational at CERN. It has a circumference of 13 meters and decelerates antiprotons, 20 million antiprotons to a kinetic energy of around 100 keV. And it increases the number of antiprotons that can be trapped per time. And it makes, previously it was so hard to convince people that we want to use the antiproton beam. Okay, what great experiments are you going to do in the particle physics sense? But now it is maybe more democratic and available to people because we can circulate 4 antiproton pulses simultaneously in the ring and distribute it to various experiments. And for antiprotonic helium, it would lead to a factor 20 increase in the annual data collection rate, and a factor 2 to 8 increase in the signal to noise ratio. So this will allow us to study more narrow resonances with higher precision than before. This facility is now fully operational. It can, in fact, distribute the beam to various beam lines located everywhere simultaneously. We therefore have no more arguments between the collaborations in terms of who gets the priority with the antiproton beam as much as before. So then our collaboration provided this spatial beam profile monitors that allow the distribution of the antiproton beam to these various experiments. And this is the X and Y profile of the beam, which shows you it's really, and this is even a single shot measurement, right? So it's really, we have, well, CERN has a handle on this, and it's really a running facility. This is the number of years that we have done these experiments and the relative precision of our antiproton helium experiments. And you see that due to the theoretical efforts coming from your community or our community, right now the theory of these transition frequencies are as good as 6 times 10 to the minus 12, almost. Limited by the 2-loop self-energy corrections. The experiment is still at a level of 10 to the minus 9, or slightly better than 10 to the minus 9. And so we really need to improve this. Okay. So the method we want to use involves firing 5 laser beams at this atom to use a kind of pump probe geometry experiment to try to improve the experimental precision by 2 orders of magnitude. And we think this is fully possible. We have also already a beamline now being commissioned at, well, it's almost well commissioned at CERN. And this is the place from which I came to this conference. So we are developing very new nice laser systems, which are more precise than before and also have a high power. We have heard several days ago in terms of Switzerland having this ultra stable optical fiber frequency system, which is now going this way to Zurich and to Basel. We would like that this is coming to us at CERN, and then for perhaps contribute to this experiment and also to the anti-hydrogen experiment. Another thing that came out very recently is that all these experiments we have done with laser spectroscopy involve putting the antiproton into a very dilute gas because of all these reasons that we have heard. But you can also be stupid and ask what happens if you put it into superfluid helium. And the point is that this is our traditional experiments where you carefully go to a low density and so on and do these foil measurements and so on. But if you increase the pressure, right, and you see it's broadening because of collisional broadening and because the atoms, well, this community doesn't need me to explain what collisional broadening is. This is good. It's really hard to explain it to a particle physicist. But if you go to liquid helium, this is liquid helium, it starts to narrow. Did you notice? So then at superfluid temperature, it very strongly narrows. And so if you have the line width here, and you have the temperature of the liquid here, this is an half matter and half antimatter atom. The line width is reducing, and at some magic temperature here, there's a sudden reduction in the line width, and you see sub-gigahertz line width. This is the PhD work of Anna Soter, who could not come this time. But this is maybe due to various phonon-atom interactions that we have not fully understood. And it opens up possibilities to use antiprotons to perhaps study if it's sensitive to condensed matter effects, phonon-atom interactions in the bulk. So one point is that people have put atoms into superfluid for many, many years. And the idea is that if you put in cesium, for example, there you produce a bubble of 1 nanometer diameter. When the laser excites the atom, the cesium atom, of course, expands, and then the bubble expands, and then the bubble sort of vibrates, and then therefore it broadens. But in the case of antiprotonic helium, this is the wave function, the radial wave function. You see there's the electron, and this is the 1s electron, and here's the antiproton. And if I fire the laser beam, I am making Rabi oscillation between these two states. Right? But you see the electron is hardly disturbed. And because the electronic cloud diameter doesn't change so much due to the thing we have also heard from Nancy, the thing is this atom is really insensitive maybe to external perturbations. So this is one outcome, recent one. So then in the remaining time, I will go quickly. What is a pion? The pion in the quark model is the hydrogen atom. The proton is a horribly complicated atom. Why did nature choose this thing to be stable? Well, there's a reason for it. But the pion is infinitely more simple compared, even it's complicated, but it's more simple than the proton. It is made of a quark and an anti-quark. And if you think about it, it's maybe in the simplest quark model. The spin of one is pointed upward, the other one is pointed downward, and therefore it is spin 0. And its parity is negative. And there is something called the SU3 flavor symmetry of the strong interaction, which says that if you have the lightest 3 quarks, up, down, strange, and change them, it's the strong interaction doesn't care. So this means that this causes that there are 9 bound states that can be generated by the up, down, and strange quarks. And if you plot them as a function of isospin quantity, that means how many up quarks or down quarks there are and how many strange quarks it contains, then you make this famous hexagonal pattern. These states are the ground states of the strong interaction of our vacuum. We live in a vacuum, the QCD vacuum. And so these states are super important to understand the characteristics of the strong interaction. And the lightest of these are the pions and kaons with lifetimes of 26 nanoseconds and 12 nanoseconds each. And so far, they were so short that you could not study them by laser spectroscopy, right? Only by the X-ray spectroscopy beginning in the 50s. Okay, so another point is that these mesons are particles with a quark and an anti-quark inside. They traditionally arise because they are the quanta of the strong interaction, the force that is carried between a proton and a neutron. And this is a kind of old way of thinking, 1930s way of thinking. But if you have a proton and a neutron, if you move them 2 femtometers away, there's one virtual pion being exchanged between them. If you are 1 femtometer from each other, there's 2 pions exchanged between them. And if you go to very short distances, then you excite more complicated quark hadronic excitations, and the force becomes repulsive. So here it's attractive, just like the Coulomb potential, but at some magic turnaround, it becomes repulsive. So this can even be reproduced by the latest QCD calculations. So this is kind of real in that sense. This pion is also important because the QCD Lagrangian contains an approximate chiral symmetry. That means that if you take an up quark, a left-handed up quark, and change it to a left-handed down quark without changing any of the right-handed quarks, the physics would be the same. But this would seem to predict that all kinds of hadrons should be parity plus and parity minus states should exist, but only one parity of each meson, each hadron has been detected so far. So it is believed that this pions and kaons are the Nambu-Goldstone bosons of this spontaneously broken chiral symmetry in our universe, and this is why it's also important. So the history of this atom is that it started in the US. After the war, people started to be able to produce these mesons using these cyclotrons, and then by putting them into bubble chambers, people discovered this long-lived atom. And the theory of the atom goes back to 1964. It was shown to be existing also in the USSR. And there were various calculations, but it was thought that this is maybe a little bit too difficult to directly detect, right? This is an explicit thing that's written in the paper. And in 1992, there was an experiment that showed that the atom has a lifetime of 7 nanoseconds, even though there's a caveat that we cannot say that the theory quantitatively accounts for the time distribution. So the interpretation was a little bit different. And then people went to antiprotons because this is kind of more rewarding. But still, the pion is interesting because if you could do it, it's the first laser excitation and spectroscopy of an atom containing a meson. The thing obeys this committee knows, doesn't need to explain that it is going by the Klein-Gordon equation, not the Dirac equation. And you can determine the pion mass very precisely. And it allows you to set upper limits on exotic forces. And you see, the pion is running around the nucleus, and the pion goes into a muon and a neutrino. And by knowing the mass of the pion, the mass of the muon, and the recoil momentum of the muon, it's possible to set upper limits on the muon neutrino. Of course, the hypercamion-Grande and this kind of stuff where they measure neutrino oscillations, this is much more precise compared to this experiment. Yet this is less theory dependent and it's independent, even though it will be of less sensitivity. So as before, this is the angular momentum quantum number of the pion. This is the principal quantum number of the pion. And unlike the previous atom, this pion is way lighter than an antiproton. This makes the atom much less stable against OJ emission. And therefore, as you can see, the lifetimes of these atoms against OJ emission are relatively short. So then, as before, you fire a laser at it. And the whole thing goes into a two-body state. And then the pion starts to gather the surrounding atoms, and then it absorbs, and then protons, neutrons, deuterons, and tritons come out. So then you want to detect now the neutron. So if you tune your laser, and your laser is in resonance with the atom, then suddenly you will see a lot of neutrons. So the problem is that there's high backgrounds, 10 to the 3 times, more than the signal from decay electrons, nuclear fission, and contamination of the particle beam. But if we are specialists, it's possible to like remove this somehow. Another problem was that we keep saying we don't have money, but we didn't have money, and therefore the laser that we are using is an OPO laser, which has only a repetition rate of 80 hertz. And then there's only 2 to 3 events per hour. But, and then we must accumulate data for months to detect the resonance. So this is the PSI cyclotron. I don't need to explain it. Here's a proton beam hitting the rotating carbon target. And then you immediately bring the pions to the helium target before letting them decay into muons. So the pions come in, they come to rest in the superfluid helium target, which we now know produces narrow resonances, right? Because of the antiprotonic helium was showing that as well. Fire a laser beam at it, and then you detect the neutron, mostly the neutrons, but also the protons and deuterons using a scintillation counter surrounding the target. And when we started this, it was really terrible because there was huge electron and muon contamination coming into the beam. So the PSI accelerator group set up this beam filter with 550 kilovolts of voltage difference, and this machine really made the difference, which allowed this experiment to work. I'm almost finished, I hope. The particles were detected by plastic scintillators, as I said, using metal channel dynode photomultipliers, two-stage preamplifiers. This kind of, if this experiment were done 20 or 30 years ago, the whole thing would have been needed like dozens of people in a huge detector, but microelectronics has improved so much that now we can do it with 4 or 5 people. So then the waveforms of these signals were digitized using an ASIC called DRS4 developed at PSI. And we synchronized the repetition rate of our pulse laser, which irradiates the atom, by dividing down the radio frequency of the cyclotron and firing it. So there's protons being accelerated in this cyclotron. This thing is going then at 50 megahertz of radio frequency. If you fire your laser, if you divide up the 50 megahertz down to 80 hertz, which is economic, okay. We only have 80 hertz, right? So from 50 megahertz, we go down to 80 hertz, and then we fire our laser synchronized to this 80 hertz. And then we look what we can see. It was very necessary to make lasers. This is a really nice telecom wavelength, but which has pulse lengths of around 80 picoseconds and 10 millijoule of power. 10 millijoule of power because the pion's daughter state, it has lifetime of only 250 femtoseconds. So the demodulation due to the relaxation due to the laser, due to the short lifetime is very high. And so we had to have very high powers to make the pion de-excite the pion. So then it was based on a microchip laser, and then we amplified it with fire amplifiers, and then we went through an OPO to make this laser pulse. And then we, by sophisticated techniques, we isolated the pions, rejected the muons and electrons from the scintillator, and then we looked at the signals of the neutrons coming out. And if you plot the intensity, well, the count rate of these neutrons, protons, deuterons coming out of our experimental target as a function of the time elapsed, okay, the peak here is coming from the fact that the pions stop in the target. This other peak that you see here is due to the fact that after 50 megahertz, there's another pion coming into the target. In between these pions, you notice this is logarithmic scale, so the background is huge here, But if you have this nice pulse laser, you can fire it in between here. And when the laser is in resonance with the atom, we saw an increase in the rate of neutrons and protons and deuterons coming out, which shows that the atom is now in resonance with the atom. There were all kinds of problems and so on with electron background and so on, but using scintillators with correct thicknesses, we were able to reduce the background enough to see the signal. And so if you still don't believe it, I can also tune the wavelength of the laser. And if I tune the laser wavelength away, then the count of neutrons and deuterons and so on decrease. And so if I tune the wavelength of the telecom laser, it was a diode laser pumping diode seed laser, then I see a resonance. And this resonance has a wavelength, has an optical frequency like that, which is close enough to the experimental, the theoretical number. It's off because we're in superfluid. And therefore, there's this collisional shift, as you saw before. But you see now that we are able to do spectroscopy of a pionic atom. The next speaker will, I think, discuss about the calculated transition energies that come from non-relativistic QED and so on. They are able now to go to 2 to 3 orders of magnitude better precision than before. So we hope to go to this level of precision in the future, though it's experimentally quite difficult. So in the future, we would like to come back to PSI, do these experiments, taking advantage of the high intensity muon beam upgrade. We will come with higher power, high repetition rate, InnoSlab lasers that do not go at 80 hertz, but something more like kilohertz or 10 kilohertz, and do these experiments. And so this is the summary. So thank you very much.
Thank you very much, Masaki. Thanks a lot for the very nice talk and results. Are there questions?
Thank you for the presentation. So I see that you are relying on detecting the neutrons for getting your signal.
And protons and neutrons, anything that comes out of a breakup.
Yeah, but don't you have a huge background come from the from the decay of the pion to a muon, and then you can have a capture into the helium, the alpha particle.
Yeah.
And then you also
Precisely.
have a huge neutron background.
Yes, precisely.
So how would you differentiate between the neutrons that come from the capture?
So initially, initially I thought you need to have vertex reconstruction and 2 layers of detectors to see the E delta E. Yeah? This would be how you would do it, or how a normal person would do it, but I cannot do it because it's too complicated and too expensive. So one did instead looking at the pulse height, the analog pulse height of a plastic scintillator with a magic thickness, which we set to 40 millimeter. And if you set it to 40 millimeter, you see that the neutron background, the neutron signal is fast, right? What you've discussed is a slow neutron. But here I'm only interested in the fast neutron. I throw away the background from the slow neutrons by using this 40 millimeter thick plastic scintillator. And then you only see the fast neutrons, which is, this is pulse height and this is arrival time, which exist in this pulse height distribution. The electron, the pi mu E background, and the slower neutrons, the thermal neutrons, will likely exist in the lower energy region here, which is rejected in this. And in this way, I do not say that this is the world's best way to do it, but in the beginning, we didn't even know whether this experiment would work or not, and even if the atom exists or not. So this is sufficient, but as you say, there are many ways to improve it if you had a lot of resources and so on.
Yes, thank you very much. Exciting developments. I had a question about this unexpected phenomenon. If you go into liquid helium, that you narrow down the line. Perhaps you mentioned it, but I mean, then you also shift the line, and you have to calculate how much the shift is. And
yes,
that doesn't make it that more complicated than it is in the first place.
So let's say it like this. This thing has no value if you're doing high precision spectroscopy of an antiprotonic atom, yeah? Because it's not necessary. But from a particle physicist's point of view, I mean, antiprotons, protons, this is interesting, but muons are more interesting. But the shorter the lifetime of the atom, the more interesting it is. And the fact that we need this decelerator device and ultra high vacuum to decelerate all these particles makes atomic spectroscopy a really narrow thing that we cannot use in particle physics so much. If you use this kind of high density target, it's possible to slow down short lifetime particles very rapidly and to study them. So this is just one technique. Of course, we'll look at new techniques, but this is the thing that allowed the pion work to work. Without this, I would not have risked it. It's just to, so this is just like work in progress.
Direct context question, Masaki. Very nice results. Can you comment on this parabolic scaling as a function of temperature? I mean, is this some kind of interaction? No.
So, Anna, I think, spent years trying to understand this because she said she doesn't want to publish until there's a theoretical understanding of it. And I said, this is not going to happen. And 3 years passed, and then we sent it and they accepted it, but still there's no reason for it. And actually, I'm happy to be here because the experts of this university and this country have can contribute, as we heard yesterday, onto this problem, and to achieve a theoretical understanding of why we have this kind of profile is very interesting. For example, it is known that if you take the viscosity of helium, which is a microscopic thing, in fact, it has this kind of shape. But we didn't dare to write it on a paper because we can only say, oh, the profile here looks like this, and also the viscosity looks like this. But yeah.
Very good. Friedrich?
So the energy level of a Rydberg atom, they're blue shifted by helium. Yeah, this is the Fermi shift. And you can, in principle, calculate it. So because you know the density,
yes,
you can know exactly what this blue shift is related to the question of Wim. Now, is your line blue shifted or is it another shift? So when you show the spectrum, you show the spectrum.
It's going to lower frequency. Therefore, it is redshifted. And then now you wonder, do you really understand normal atoms, right?
Yes, that's okay. So that's interesting.
It happens very often that there is a model which explains something, but then if you change the particle, it changes.
A short question, can you chop the pion beam? Say you have a 10 kilohertz laser, why not have a 10 kilohertz pion beam? Can you chop the pion beam? If you have a 10 kilohertz laser, what would you chop the pions so that you have a 10 kilohertz repetition rate?
That is a good question. So this is a cyclotron, and you put in a continuous beam into it, and it's accelerating a continuous beam continuously. So it's very different from a synchrotron. This is the advantage of this kind of machine, that it's like a CW laser that it's continuously coming out. We are trying to request PSI to install like a chopper here. We cannot chop the beam so if the acceleration, the thing coming out from here is 620 high energy, we cannot chop that. So you can try to chop here, right, when the energy is quite low, and then carry out the experiment that you asked for. But the problem is we are not at all important experiment at PSI because downstream of this is the neutron people and so on, the other users. And if we chop the beam, they get influenced as well. So you need to find a compromise where you chop the beam, but you don't disturb the other users.
But there are several experiments that are looking for a shared pulse beam at PSI. So maybe that could be.
Yeah, so if there is enough interest, I mean, you have to understand that a lot of people thought this experiment is not going to work. Come on. So now that we understand that it's kind of working, then we can discuss whether we are allowed to disrupt somewhat, a little bit the other users.
Masaki, if I can comment on this, you know, Mulan experiment, PSI, they used actually a deflector. What you do it downstream, right? So you don't perturb anyone. Here, you would put a deflector, a high voltage deflector for your pion beam, right?
Yeah. So
and then have it just on the target when you need it. This was done for muons at 26
the
MeV
problem
over
with,
C.
the problem with pions is that it has to be much more sharp. So this was discussed, and it was said that with pions, it's like to switch within a few nanoseconds, such high voltage is not so feasible. With muons, of course, it's a microsecond, so this is possible, but here not. So the accelerator people said it's most easiest to change something upstream.
Okay.
But this is under discussion.
Very good. So Thomas, please.
Yeah, thank you. Yeah, first of all, thanks a lot for very interesting results. And it's great to see Elena at CERN, at AD working now. My question would be, obviously that has improved substantially the efficiency of the experiments. Now, to make the full story would, of course, be great to have also extracted antiprotons and maybe even cooled antiprotons. Are there any plans with this regard?
I'm not speaking for CERN, but I think the idea is that this kind of experiment facility is best to do at GSI FLARE. So that is the thinking so far of the community, but that to be discussed. That has there was an agreement around 2005 that this will do pulse experiments, and then the CW experiments will be done at the GSI. But yeah, but it's yeah. But okay, I can only comment like this. I'm supportive of whatever the community decides.
Thank you.
Yes. So are there any questions? Yes, here.
So I was just wondering why you exactly shoot your laser at this exact 80 hertz.
Okay. So
you have a repetition rate of 80 hertz, and wouldn't you like to shoot at every pion, creating a pionic?
yes, but you see that so lasers have there's a limitation in terms of how much power you can produce out of a laser, and this happens to use something called medium YAG, which is a kind of crystal. And if you pump it too hard, it starts to do some ugly effect called thermal lensing. And when this thermal lensing becomes very bad, then you start to destroy all the crystals upstream of everything. And I have done
then
this.
Then you can use a thin disk.
Huh?
Then you can use a thin disk technology.
What?
You can turn to thin disk technology.
Thin disk technology,
like what we do.
Yeah. Thin disk technology is very nice, but the single pass. One of the issues is that the single pass gain is relatively low. And in your case, there's a microsecond lifetime. In this case, I have to fire with 800 picoseconds. You can try to do something, but in this case, I needed, well, this experiment, this is in a concrete, it's in the outside. So to use thin disk here, this is like suicidal, so you do not want to do that, right? Yeah. And also the infrastructure.